All right, let's go over this test fairly quick. Then continue into chapter 15 to do bending stress and shear stress. We've done bending stress a couple times, so that should be pretty quick. We haven't done shear stress at all. So we got to get that one down because the three things you're going to want to know if something is safe or not is bending stress, shear stress, and deflection. Those three things. So, or if you're going to design, those are the three design parameters. All right. So we had to do the statics first. I think everyone did the statics just fine. The forces up and down were equal. So AY was 0. The moment out here was 12 kip feet. This is fixed, cantilevered. So this is where it carries the maximum moment, is right here. We know that all cantilevers is going to carry the maximum moment here. So once you have that done, then you just do your shear diagram, right? Goes up to 4K, following that one. Nothing happens, comes down to 0, and then nothing happens. So in this region, nothing going on. As far as the shear goes, 0. So maximum shear force was 4K. And then we would use that to get shear stress, which we're going to do after we go over this test. And then the maximum moment down here, starting out here, it's 0. It increases because we see this plus. Remember that plus is the slope. It doesn't necessarily mean that the moment's positive, right? It just means the slope is positive. So it could be down here, but it starts from here and then slopes up. So it's definitely up. And we know that this kind of a deflection is a positive moment. Okay, so up, 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 and then nothing changes. That moment, if you calculate it anywhere along there, is going to be the same. So, because these two are fighting each other moment-wise. So that's a little bit unique and kind of weird. But if you do a moment here, do a moment here, do a moment here, you get the same moment because they oppose each other at the same rate. You could test that by sectioning. And there's several folks that did that actually. Sectioned it a few times and got the same number and went, oh, that goes straight across there. Yeah, yeah. It's kind of weird that it doesn't continue up. So. But yeah, I think, I'm not sure anyone got that one wrong. So that was good. No, there was little mistakes all the way through. Everyone got their own little mistake. Here's a perfect example of the most common mistake was finding this location where this crosses 0, because that's where maximum moment's going to be. So again, I think everyone did the statics correct, 24 and 16. So that's good. So then the shear diagram goes up for the 16 across because nothing's going on, comes down 8 to 8, right? So that's all positive up here. Then it continues down at 4 kips per foot until it gets down here to minus 24, and then 24 sends it up. So that's good. We do need to know where this X is because that's going to be this maximum moment point down here. Where the shear crosses 0 is maximum moment. And since that's what we wanted to know, we had to find this location. So the way to do that is similar triangles. So the concentration for this distribution is here, and that's over here somewhere. It's not where the 0 is. So you just have to go through this ratio of big triangle. So here's the big triangle that we know everything about, right? We know its run is 8 feet. And we know its rise is 8 plus 24, 32. Right? So we know 8 to 32. So that's this one, 8 to 32. And then this little one is X to 8. This little triangle here, X to 8. So that gives us an X value of 2 feet. And then from that, you can go up, you could section it and just do a moment there if you wanted to. That's fine. I actually do areas. So I did the rectangular area, this area, 16 times 4, because this is 4 feet. So that's that one. And then this little triangle, 1/2 the base was 2. So 1/2 of 2 times a height of 8 gave me 72 kip feet for this max moment. The other point for the diagram to be accurate would be here, where it transitions from a straight line to a curve, and that would be 4 times 16 to get this moment. So this Vmax, we will calculate, whoops, they don't use that. They use this shear stress from that. And this, we will calculate bending stress from MC over I. So that's where we're headed. Oh, remember, if you did the section, like this is the beam, if you come up with a negative 72, the internal moment resists that, right? Yeah, so that's the internal moment resisting this one, and it becomes positive. Yep. That's all right. We haven't done enough to get all those fine details. You had the number right, so it would have went into bending stress correctly. So that's a big part of it. Yeah, we know it's positive. So the other reason you know it's positive is because of concavity. So just thinking about deflection. All right, next one, same kind of problem, very, very similar. Had to get the statics right, which was 19.5 and 16.5. And then the shear diagram, which comes up the 19.5, comes down at a slope, pretty good slope, and then continues on at a little flatter slope. So the smaller the number, the smaller the slope. Larger the number, the larger the slope. And these are all pointing down. So that's why it drives the graph down. And it's the same kind of problem. We had to determine like, oh, where's that crossing to get the maximum moment? I know the moment is a positive curve, and then it changes to a little less positive curve. So that's positive curve, little less positive, little less positive. So it's curling over. And then again, positive getting less positive. And then maximizing where the shear goes to 0. So again, you had to find that X location, had to use a big triangle and a little triangle. The big triangle is 24 by 6 feet. So the difference between these two, 24. Yeah. 24.5, right? 33, and like, I didn't see where you got that from. Because your numbers were right. Like you had the 7.5 and the 16.5. So how I do that is if I do it in my head. Like if I don't use my calculator on some simpler math, but you know, add 7.5 to 16.5 in your head, you can make that mistake. From the ratio? I remember that. I'm like, did you do it right now though? Yeah. Yeah, I saw that too. I went, oh, I don't know how he got that number. The ratio looks good. Uh-huh. Oh, yeah, I did notice that. I think I put that in the note to you. You just transposed the number. Yeah. That's the only thing that took like 3 of you out of getting 100% was those little kind of mistakes. Yep. Yeah, and then I did it. For some reason I put 17.5 in here, and that's supposed to be 12. So it's just a good thing we don't work completely alone. Like, it's not, the only time you work alone is like on an exam. When you get out and you're working on this kind of thing in industry, you will not be alone. Yep. Yeah, and then I did areas again to get my moment. So I just did a rectangle 2 times 7.5. And then I did this triangle, but I did it incorrectly the first time. It's 12, 1/2 and 2. And then I did this little triangle, 1/2, the X value and 7.5. So gave me 3403 kip feet. So that's going to be the M max for bending stress. And this, the largest number in the shear diagram, gives us shear force for shear stress. All right. One more. I actually tried to do it like in this position and I screwed it up too. So it's probably best to flip it over, get it sideways to do it. With these kind of problems, it's always good to think about, like, it's essentially a cantilever type of problem, right? Because it's fixed here. So we have to calculate the moment down here, which I got as 87.5. And then we have an X force of 5. So then flip it around and just follow the forces. X force drives it down, nothing happens, and then we have a slope bringing it up to 0. You just have to continually remind yourself that this is fixed here, and this is fixed here. So then to draw the moment diagram, you have to be careful with, this is all negative slope. So this is horizontal, getting more negative slope, more negative, more negative, more negative. It's definitely going to be that convex down. And then we know the maximum moment is over here at this fixed. So all this negative then creates a negative slope. So it only returns to 0 if it's a free end. This is a fixed end, so it's definitely not returning to 0. So it's going to look something like the blue. The squiggly lines was my attempt to do it in this position, which I just could not figure out. So finally I went like this and went, oh, yeah, that makes a lot more sense. Here. Yeah. Yep. It should be. Yeah. So for me to draw it correctly, this would go just like this. Yep. It should be tangent, because infinitely close to this point on this side, infinitely close on this side is the same slope, right? So you have the exact same slope coming in, the exact same slope. It should be tangent. Yep. The only time it's not is if there was like a, let's see if I could do this here, spike, some kind of spike right here, which, would have shifted this to here. Then you have, 2 different slopes coming into each other, and that's going to not be tangent. All right. So important part, V max 5K, M max 87.5. Oh, that just what is wrong with this picture? Yeah, you guys, you haven't had a whole lot of them, so I was impressed. You guys did well.
Anybody get 100 on the first exam?
I'm trying to remember. I think again, it was just super close, little mistakes. Somebody will get 100 on the final because the final is comprehensive and it's the typical problem out of the chapter. So not a difficult one, like a very standard problem. So for example, like out of this chapter on the final, you'll see something like that very first one. Actually, the very first one was a little bit tricky. I thought everyone did fine on it, but you probably won't even have one that has an X value in it. Like it's just super straightforward. What I want to know out of the final is if you understand the big concepts of the term, right? Do you know what bending stress is? Do you know what a moment, an internal moment is? Can you draw a diagram? You know, all of those very big concepts, that's all I focus on.
We're going to do questions like on the first example, tensile load and all that stuff.
So out of each chapter, you'll get one question. No, it could be, no, it'll be a diagram, like you'll have a drawing. Yeah, so like out of that chapter where we did the stress considerations. So out of there was things like Poisson's ratio, there was things like tensile stress, you know, just something being pulled, or compressive stress. It'll just be a simple P over A problem that you have to figure out. I might bundle it into like, is it safe? Like, okay, I'm gonna have you calculate stress, but then I'm gonna have you comment on it. Like, is this good or not good for wood? Yeah, yeah. So that's the big thing about this class is you should calculate numbers and then also make decisions based on the numbers. So
We're gonna go over the homework because I got like nothing with points to look at.
absolutely. Maybe we should do that before I go into stresses. Which one?
I think it was. I think both of them. I have no idea how I could have messed up on 14.3 unless the IX was different than I used the numbers.
14.3.
14.3 and 14.5.
Okay, let's do 14. Well, let me look at them.
14.5.
We'll do the one that is going to be most like here.
14.5 gave us beam dimensions. Like
oh yeah.
The size. It's 3 inches by whatever.
Let's do 14.3. Yeah, that's a good idea. That's perfect, actually. So 14.3 says a W 18 by 71. Has a superimposed uniform distribution as showed 400 pounds per foot. I'm gonna draw it. Calculate the maximum bending stress. Be sure to include the beam weight. So we're going to add the 71 and the 400, right? So the total distribution is going to be 471 pounds per foot. Did you do that, Nick? Oh, how did you not get this right? 28 feet. That's fine. That should work. So we have half of it going here, half of it going here. What do we get for the, so I'm going to cross this out because I don't want that to be too confusing. We have one distribution, 471 times 28. Oh, calculator's freaking out. We have a total load of 13,188. 6,594. And those are pounds. So I'm gonna do shear diagram. I don't know that we had to. Probably can guess where the moment is. But I'm gonna expand the problem a little bit. Why not? What's the shear do? Goes up. Yep. And then. Yep. And then comes up the same amount, right? So the exact middle is the maximum moment. What's the moment do? Plus, 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 minus, minus, minus. So plus, plus, and flat, and little minus, and more minus. Yep. With the max moment there. So M max should be 1/2 the base times the height of the shear, right? So this is 14 feet. This is 6,594 pounds. So 1/2 14 feet, 6,594 pounds. Is that what you got, Nick? 6,594, 14 times 0.5 times 46,158. 46, I'm gonna do 46.158 kip feet. So this is the area method, right? 1/2 the base times the height. It's using that area of the shear.
So like I did it with the redraw. And it would be 471 times 7 plus 6,594 times 14.
Oh, you sectioned it.
Yeah. There's only 4 numbers. I got 89,000.
All right, so it's gonna be the 471 times 14. Right? 471 times 14 is that. And then it's times halfway because you're concentrating it. No, 471 times 14, that's the concentration. Times 7 is the lever arm. So there's 3 numbers when you do a moment of a distribution. Yep, you had to concentrate it first. 471 times 14 times 7. So.
Also, you would include because I thought you didn't have to use the force if it went directly through the exact spot.
So if you're doing it by section method, which is what Brian was talking about, section the beam at the halfway point to get that moment. No, because you got to take the 6,594 times 14 away from it. Because that's there too. You got to include the distribution. Yeah, you got to include everything if you section. You get a negative, but that's because it's the beam, and then the internal would flip. Yep. 46.54. Yep. Boom. Yeah, if it's a triangle for sure. Like it does get complicated if it's like parabolic in the shear. It's like, ugh. But yeah, it's not bad. It's not bad at all.
There wasn't a spot for this.
Oh, no, I probably forgot. So yeah, I'll put it up. If you have it physically, I'll take it that way too. All right, so let's do bending stress because we have the beam, right? It's an 1871, it's a structural steel shape. So that means, okay, well, we found the moment, but is that cool or not cool with this beam? Like, that's why we're doing this, is to determine if this beam is good or not good. Okay. So the equation for bending stress is MC over I. And we know it's a W 18 by 71. I'm just going to draw it. And I know it's approximately 18 tall, but I need to look up and see exactly what it is. Perfect. Yep. Is that IX? Yep. And we're going to assume it's in the strong position because they didn't tell us it was not in the strong position. So this is the strong position where it gets loaded against the x-axis. So that's why we use IX. C is the distance from the neutral axis to the outermost fiber. And if you have a symmetrical shape, then it's the same top and bottom. If you have an asymmetrical shape, then you need to use the largest C value. So C is half of the 18.5. So the equation is moment. We know that's 46.158 kip feet. And it's super important to write the units in because you'll have some conflicting units. Because I'm going to put in half of 18.5, and that's inches, 9 1/4. And then I goes in its units. But we need the feet and the inches to combine above to eliminate 2 down below. So we're left with kips per square inch. So we have to get rid of this foot. There are 12 inches in a foot. So now that unit can go away. So I have inches squared, inches to the 4th. So that leaves me inches squared below and kips above. So this is going to be in KSI, which is fine. I can use KSI or I can get it to PSI. Back of the book could have either one, actually. So you just have to be aware of it. Really important, because when you get out there and start working with some tables other than the book, those units can come to you in KSI, PSI, newtons per meter, all kinds of crazy units. So you just have to really be careful. I get 4.379, 4.38. KSI, which is the same as what? 4,380 PSI. Okay, so structural steel, if we don't know its exact properties, structural steel typically is a A36 steel. 36,000 yield. So we're at 4,380. We're magnitudes or factors of safety under the 36. So if I take 36 and divide the 4.39 into it, that's 8.22. That's a factor of safety of 8 on this design. So that's good.
When you did the moment by the section, you go over how you got that number.
Yeah, so the moment by the section up here, I'll write it. So the moment, and I would write it, the moment at 14 feet, because that's the halfway point, right? It's going to be 471 times 14 times the lever arm, which is halfway, 7, because I'm doing the moment here. Got to concentrate this whole thing to right here. You do to calculate, yep, to calculate a moment, yep. And that is going this way, which is positive, and then I have to subtract the 6,594 times its distance of 14. That'll give me the moment at 14 feet. Gives me the beam moment. I have to flip it to get the internal resisting moment. So if I did that right, it should be the 46.158 kip feet. Right, same as this one down here. Area method and section method.
Yeah, that's where I went wrong, because I was treating it as though it couldn't move and it was just static.
Yeah, yeah.
Times zero, there'd be no lever arm, so it wouldn't move.
Right. All right, so that's the bending stress. So the other one we have to work with is the shear stress, and that's going to be from the shear diagram. It's pretty easy that we have V max at 6,594 pounds. But the other thing we need is the shear stress. We did the bending stress, it's good. So the logic or the talking point is always design in bending stress, check in shear stress. So this is really what's really important to us. This is the one, this is the control often is the moment. Shear is rarely the control. Like you have to have some crazy reactions to get a shear stress that's stressful or worrisome. So there's multiple equations for shear. And we're going to focus on the shortcut equations because those are the ones you're going to use. So these equations are right there. This is what's called the long form, and this you'll seldom use, very seldom. I'll go over it probably in a video just so you know. Everything's pretty straightforward except for this Q thing. This Q thing is called the statistical moment. And it's a little funky, but most of the time we don't have to use it. If you're working with an I shape or a rectangle or a circle, there are shortcut equations that get us out of having to run Q because Q is such a pain. So we're currently working with an I shape. So the shortcut for that is VDTW. V, shear force from our diagram. And DTW is from the W shape. So I'm going to rewrite that equation. Oh, that's the wrong one. Oh, I see it down there. There we go. So the shortcut for shear stress for a I shape, and I try to always kind of put a note down what shape I'm working with, is V over DTW. The D is from the back of the book, and it's the depth of the beam, 18.5. So both of these, we just get out of the back of the book from the little diagram on the W shapes. So, and show that to you. And then I'll explain like how we get away with this shortcut. So D, right? And then TW is the thickness of the web. This is called the web. This is called the flange. Thickness of the web. So essentially the area that we're using down below is the depth times the thickness of the flange. It's this long rectangle right in the middle. Well, that long rectangle is like 96% of the shear strength of the whole thing. The flanges don't help us much at all. So that's how they do this, is they just essentially give us an area that is the depth times the thickness of the web. So the depth is 18.5. And the thickness of the web is what? We look it up. 1871 DTW is TW thickness of the web 0.495. And then V, shear force, 6594. Cool. Vmax for sure. Yep. You always want to use the maximum force off of the shear diagram. Shear force. FV is shear, this is shear stress. Sorry, shear stress. V is shear force, right? That's the force we got from the diagram. Then this is calculating the stress. It's actually full distance. D, yep. So it's here, I'll show you. It's this. It's this area, right? It's that middle rib, full length. That's what's doing all of the resistance in the shear. These flanges, hardly doing a thing. So what do we get for that number? Yeah, and that's what kind of unit? Yeah, pretty small. 720.10 PSI. I mean, that's compared to, what do we get in bending? Yeah, 4,300. It's almost always not a problem, the shear, but we just check it every time. So if it's not a W shape, and if it's a piece of wood, a timber, that's our rectangle. That equation is even simpler, 1.5 V over A. So this one typically is wood beam. This one is W shape. This one is round. So those are the common shapes that we use a lot. If it's something else, then we would have to go to the long form VQ over IB and actually calculate Q and actually have to calculate I, and it is a way longer process. So we did I, but that was like 8-9 weeks ago, how to calculate I on a complicated shape. B is the base at the point that you're calculating the shear stress. And when we calculate shear stress, we are calculating it at the neutral axis. That's where it's maximized. So
All those V's are all Vmax.
those are all Vmax. That's correct. I should actually be writing that. Yep. A is area, correct. And then this is D, and then TW. So these are two different things. So this essentially gives you an area. This is an area. This is an area. No real shortcut for the bending stress. MC over I is what we use almost all the time. If it's a common shape, like a W shape or something, we can use an SX value. So it can get simplified. I think it's just complicating life because you have to learn, oh, now I have to learn what SX is. Well, SX equals I over C. So that's why SX is down below IC, right? So it's essentially just taking two constants and turning it into another constant. It's like, I don't even know why we do that. It just seems to complicate things, but in the back of the book for structural shapes, there is an SX value. So you can just use the moment and the SX value to get bending stress. Or you can use MC over I, but they do talk about it and show it to you, so. Yep, always. Yep. So that's the two stresses that we want to do on anything that we're calculating and trying to determine if it's good or not good, safe or not safe. To design, we just put in given values and kind of work it backwards. So we use this equation to design. So design means I don't have the beam, right? So I can draw a problem. And I'm going to put 4,000 pounds. Whoops, forgot a zero in there. I'm going to know my span. I'll say it's 10 feet. And I want to know, like, wood beam. How big? Right? That's design where I got to know what material I'm working with. Wood, steel, whatever. But I don't know the size. Like, how big of a beam do I need here? Okay. So we design in bending stress. That's the tool we use. We'll check it in shear after we choose, we'll check it. But to begin with, we design in bending stress. Well, we don't know I, and we don't know C because we don't know the height of the thing. So that's where this is quite handy in that, oh, this only has one unknown because I can calculate the moment. I have the load. You got to have something, got to have the load, got to have the span. So some of that has to be determined. So how much load do we have at each reaction? We have 2,000 here, 2,000 here. Where's the maximum moment? Yep, shear goes up, over, down, like that. And then the moment goes up and over, it's right there. So it's right here is where the moment is. And how big is it? Moment here, 2,000 times 5. Right in the middle. Right, that's where the max is. So it's going to be 2,000 times 5. What's that, 10,000? So then I know it's wood. I'll say it's Doug fir because we would have to know what it is. What's the maximum bending stress for Doug fir? Well, we can look that up. So when you're designing, you work with maximums on the stress level to take that out of the equation. So bending stress, F sub B, Douglas fir, 900 PSI. So the equation, MC over I or M over SX, I know the maximum is 900 PSI. And I know the moment is 10,000 foot-pounds. And I don't know the SX. I have per square inch over here. I have feet here, so I need to convert that foot to inches. So that's a factor of 12. Now I can calculate my SX. And that's how we'll choose the beam. So a little algebra, this moves over, the 900 moves down. So it's 12, 10,000, and 900. I get 133.33. And the units, the feet cross, so I have inches above, and then I have pounds per square inch down below. So the per square inch flips up, and I should be left with inches to the third, which is a weird unit, but that's the SX unit. Yeah, so that's one of the things that's in the table is this SX value. And it's the only reason it's in there is for the design purpose of trying to choose a beam. So I'm going to go to the wood, structural wood shapes, trying to find it, can't find it. There it is, 495. My number is 133.33 for the SX. So there's SX showing up. So looking down, here we are at the 4x material. We're still not there. So see if we get larger wood pieces. 4x 133, is there one in there? Oh yeah, there is, you're right. So 133 is the minimum. We can go over it, we can't go under it. So this is minimum, smallest wood you can use, right? So 133 does not show up in the 3x material, but it does show up in 4x material. 136 would work. And with wood, you can go as close as you want. All the factors of safety are they're already worked in. You don't have to add a factor of safety. So that means a 4x16 would work on the problem that I made up. 4x16. Pretty big chunk of wood. 16, 4, pretty huge, right? So that's how you make the choice. That's our first little design process. You'd want to check it in shear. And then once we get deflection, you want to check it in deflection.
Is this, are the SX numbers in the back of the book, assuming that you're going to put the long and vertical?
Yes. So that's super important. The whole table is built off this position, right? So if this thing was on its side, this would become the SY. It would go in a different, it would be different. So all the tables are built on the strong position of whatever you have. So for wood, we just don't side load it ever, so you don't get an SY. But for like W shapes, they should give you an SY. They do. So they give you SX and SY. So that's all based on this position. If you're working in the normal position, load coming down onto the strong axis, then that's SX. If you get a side load, which we do get with steel, then you would use the SY. Yep. Some crafty engineer flipped it on its side. Thank you very much. Some kind of life test or something. I don't know. That's right. All right. Yep, we are good. You have some homework. I'm going to post it up right now. Let me see. Assume the timber member problem 14.2. Oh yeah, use the simply supported beam with a 12-foot span carrying uniformly supported load. Given load including the weight of the beam, calculate the maximum induced bending stress. So that's this one. So you had to find the neutral axis location. You had to find the inertia. And then you had to go through the whole thing to calculate your maximum moment and then bending stress. No.
In that case, the C value would just be the Y bar, right?
It's the largest Y bar because there's two of them, right? There's this and this.
I did it from the bottom, so it would be the one.
Correct. So that's what's important. C is the largest distance. If it's not symmetrical, there'll be a shorter C value and a larger C value, and you want to use the largest C value.
I had to look it up, so I want to make sure that like, you like have for the area moment of inertia, you add, right? I think that's how I did it.
For the area moment of inertia, you add to calculate the area moment of inertia.
I think I used the areas of the like.
Yes, you do. That's right. Because they're both solid.
333.
Yep. And then you had to use the transfer formula. Yeah, you would have to, yeah, that'd be a long problem. Super long. Yeah, so you calculate the inertia of the top rectangle, you calculate the inertia of the bottom rectangle, and then you have to transfer that distance. So this is the D distance. That's going back in time right there. Yeah, exactly. So you can only add inertias if they line up. Like this one, the inertia here and the inertia of this plate and the inertia of this plate all line up. So you can just add them. But on the X, nope. You have to transfer them. Yep. You have to transfer it.
We did the whole thing with the new numbers because I didn't use the distribution, and now it's wrong still.
That's brutal problem. I should work that. Like, and record it so you could walk through it. Yeah, that's like the entire term of strength of materials in one problem. Yep. Probably not giving that to you on the final. Or I could just give you that one problem. That one problem on the final and you're done. Yeah. Yeah, don't miss. Oh, and yeah, it's gonna have a little statics in the beginning too. So it'll be statics too. Yeah. That's the real problem though. I mean, it's, you know, the good news is you're getting paid fairly well per hour to work the problem. So you take your time and you get it right and you have other people check it, but that is the problem. Yeah, exactly. Let's see here.
That's probably why we use standard shapes that have high axes given.
Think I have maybe. You know, you don't. Exactly.
You happen to know that the longest descent possible problem? Does it any trouble?
I've just had a few that haunted me. So I kept going back, you know, over it and over it. And then if you find a mistake in that process, then you're like, oh shit, there could be another one, you know. So there, I've had a few that I've spent days working on and just walked away from it because that helps. Like that helps so much. And then just come back to it, work it again from the beginning. So yeah, there's been a few, and there's always some that just change as you're going through it. Other people change it on you. And you're like, okay, I already had that one figured out. Now you guys are adding 4 pumps and a tank. It's like, really? So they just don't get it. Yeah. Yeah.
Yeah, on the homework yesterday, in plane surveying, first one. Basically, like what we had done packaging.
Yeah.
Not problem 7. So that one, I was off by 0.03 on my coordinate.
Ooh.
This was the end of 1,000. Yeah. 1,000 and 1,020.
Wow.
The whole package is azimuths.
I left mine in azimuths. Screw bearings, bro. Who uses bearings?
I even asked him about it today. He was like, I encourage you to never use bearings. Like, That's what all the homework problems is.
Yeah. I was gonna show you the one I'm doing right now, which gave me some headaches, but I don't really have a great picture of it. Which is really weird because I usually take a lot of pictures, but I don't think I actually see it in any of these. Nope. I'll take some pictures of it and show it to you. Yeah.
I was looking at the curriculum.
Uh-huh.
They said